You've heard the term Timken Bearing Conversion over and over again, I'm sure, in regards to your Harley Davidson. In 2002, the main bearing in the engine case was changed from a Timken bearing over to a roller bearing. You've heard that term, but you may not understand exactly what a Timken bearing conversion is or why you need it. In today's video, I'm going to explain all of the dynamics and the forces that are going on in your engine case on a performance build, how that affects the crankshaft, and why Timken bearing conversions are a good idea for your performance engine. So stick with us. All right, as you can see, I have a camera on my head. You guys asked for it, so you're going to get it. It'll give you a little close-up perspective on the parts and exactly what we're talking about here, and see everything that we're doing. This engine in particular is out of a 2007 Electra Glide owned by Dorothy and Daryl out of North Georgia. We're building them a Skunk Works 107. And again, this is part of our M8 versus twin cam series on comparing the two engines and also showing Skunk Works build from the bottom to the top. So the first step in that process is going to be to do the Timken bearing conversion on this case, which I'm going to show you how we do that, or one way that it can be done. But first, let's go through the actual components of a crankshaft or flywheel assembly and detail each one, and I can explain the differences between a performance one and a stock one. So before we go through the individual components, let's understand some of the forces that are at play inside this engine case. We have our flywheel halves here. We have the connecting rods. This is a custom built flywheel, obviously, H-beam rods. The two flywheel halves. And these two halves are joined together with a single crank pin. So if we were to take this apart here, this is a stock connecting rod with the crank pin that you would see in here. Now notice that this crank pin is hollow. That's a key thing that we'll get to in a second here. So this is hollow, and you have a single rod, and then you have a saddle rod that goes over the top, just like this rod here, and that's what forms your rod assembly. So these two halves are pressed together onto that single crank pin. You've heard the term sprocket shaft and pinion shaft. This is your sprocket shaft side. This is your pinion shaft side. So if we were to look at it on the case, you can see here your pinion shaft side is what is inside the cam chest. Then your sprocket shaft side is what is inside the primary. Now let's explain some of the dynamics that are going on a crankshaft. Considering how this is pressed together, two halves, independent of each other until they're pressed together. Consider the forces that are at play on the flywheel assembly. The thing about the laws of motion, Newton, I'm not going to get too scientific, but one of Newton's laws of motion is that objects at rest want to stay at rest. Everything moving inside this engine essentially is a rotating assembly or oscillating up and down. Every component in the engine is doing everything it can do to work against you. It's working against forward momentum. So let's consider the forces that are at play on these halves. On this side of the flywheel assembly, this is where your compensating sprocket is. This is where your front primary chain sprocket is. This side independently is responsible for driving your primary chain, your clutch basket, and the rear wheel. That's a tremendous amount of force on this side. Of course, the more throttle you give it, or the more decelerating that you do, you're putting more pressure on this side. Now, an interesting thing on this side, this is what is driving your cam plate. It goes through your cam plate. It's driving your oil pump. It's pushing lifters and driving the cams and also opening the valves. But think about this for a second. Consider how much force, all the combustion pressure from the engine is then being transferred essentially through this side of the crank to drive the back end. That's a tremendous amount of force. And when you compare this side to this side, yeah, sure, it has some parasitic loss, some resistance to rotation, if you will, but by comparison, nowhere near what your left hand or sprocket shaft side is going through. So to a large degree, this right-hand side of your flywheel assembly is pretty much just along for the ride. Now, if you consider the stock crank pin being hollow and then the fitment within it, when you start getting into custom flywheel assemblies, with ours you'll see that it's plugged. You'll see it's not hollow as the stock one is. You'll also see that it's welded. As this assembly is rotating, the pressure revolves as the flywheel is spinning. But then you also have the tremendous forces on this side, with this side kind of just going along for the ride. So it's quite possible that these flywheel halves can shift and scissor in this direction. They can also flex in this direction, inside and out. Okay, but then we've talked about runout. Now, runout is several places you can actually measure crankshaft runout. First off, you have your bearing surfaces here where the flywheel assembly is supported within the case. Then you have sprocket shaft runout measured here on this end, and then you have pinion shaft runout on this end, which is critically important when we're talking gear drive and you know, high-end cam plates, things like that. That pinion shaft runout is important. And reference our other videos on runout and sumping. I did some videos on that also. So it is entirely possible that this flywheel assembly, when measured at the bearing surface, can have virtually no runout, being that it's been trued. But then these shafts can also be warped, bent, producing runout at the tip that doesn't necessarily exist here. Now, this is a very rigid structure, of course, and that's tough for it to do, but it is possible. So when you are talking about the runout of the flywheel assembly, you have this runout here, but then you also have this pinion and sprocket shaft runout that you have to be concerned with. Okay, so Timken bearings, considering all the forces that are on this crank, considering that it's shifting back and forth and it's rotating, and you have these forces that are enacting on it in both directions as it rotates all the way around, we want to try to secure this flywheel inside the engine case as tightly as possible. And we want it to be secure independently of any other components. That's going to ensure that this flywheel's not going to shift axially left and right during its operation. We want to try to make this independent of the other components, the compensator and things. So let's take a look at what a Timken bearing is. It's two tapered bearings. This is exactly how it comes out of the box. You have a spacer in between. Then you have bearing races here. This isn't any different than on older cars when they, back used to have Timken bearings, and then you had tapered Timken bearings on older motorcycle wheels and things like that as well. So the idea is that both of these races being tapered are pressed into the engine case, and then you have these two tapered bearings on either side. This bearing being pressed onto the sprocket shaft of the flywheel. This side of the bearing comes in the opposite side of the case and is then pressed in, and these two bearings mate inside the case pretty much like that. Okay? Just like that. Now, there is a spacer that goes between these bearings, and when you hear people talking about bearing in play, what that's referring to is when you press this assembly together and this end goes into the case and all these bearings are pressed tight in together, there's a spacer that goes inside here. And you're measuring in play, you're seeing how much that crank shifts back and forth inside the engine case. Again, independent of any other component. That is important. That holds the crank in its perfect geometric center line to the case. Now, understand this measurement is taken, and we only want this crank to move somewhere around 2 to 3 thousandths of an inch. 2 to 3 thousandths of an inch. That's a very, very small and precise amount. But you need a certain amount of, not necessarily preload on the bearing, let's call it free play on the bearing, so that it rotates freely without any friction. It doesn't build up heat. Now, the stock bearing I'm going to show you in a little while. I wanted to leave this case assembled to show you how the flywheel assembly acts inside the case. It is a roller bearing, an INA bearing, it's a manufacturer. INA bearing, you may have heard some people call it that, but it's a roller bearing. That bearing allows the crank to shift back and forth. So remember, here our end play is 2 to 3 thousandths of an inch, depending on how it's set up. Now let's take a look at the stock assembly. That's a considerable amount, 1/4 of an inch, give or take. So remember, I said that we want to be able to set, for the most rigid structure, we want to be able to set that crankshaft in play so that it's not reliant on any other components to hold its center line. That's where things are different on the stock roller bearing setup. You can see how much the crank shifts back and forth. What holds the crank on its center line, when you add a spacer, on this side here, you add your spacer, then you have your compensating sprocket and the big bolt that holds it in. Of course, your stator is around here and your rotor is here. It's the combination of that spacer that's there, the compensator, and this bolt that holds the crankshaft in and tries to keep it from shifting. But keep in mind, we're relying on multiple additional components to hold that crankshaft in place. Consider all of the stresses that are taking place on this crank, and you can see how that is nowhere near as stable or reliable assembly as it would be with a Timken bearing. Now let's think about the other forces as well. So we have that roller bearing that's on the inside of the case, and there has to be a clearance for it as well. As the forces during the combustion cycle, the crank's going down, it's pushing on this side hard, and then it's coming back up, and the forces are pressing on that bearing repeatedly over and over in that particular area, and we're depending on all of these other components to hold it straight. And you have these lateral forces back and forth. You have so much going on inside of this thing, rotating at 3, 4, 5, 6,000 RPM on that roller bearing that's not necessarily precision fit. Now with a tapered bearing like this, then you're able, when you dial that in, the bearing itself is much more stable. It has much more surface area, being that it's on a taper, and it's a cone shape. So that cone is going to centralize those forces and that load and help maintain it over time. That is the reason why a Timken bearing conversion is such a good idea. One common question about Timken bearing conversions is, why don't you do it on both sides? Again, let's go back to the forces that are on the crank. The majority of the forces during the combustion process are occurring on the sprocket shaft side. The majority of the load is on the sprocket shaft side, because that is the side that is driving the rear wheel. Again, the pinion shaft side, to a large degree, yes, there's load share going on there, but to a large degree, this side is not going to see the same forces, jerks, that this side is going to see, because this is connected to the rear wheel. And that's most commonly why you only do a Timken bearing on the left-hand side. Now, in extreme applications, yes, you can do a Timken on the right-hand side, but it is a very expensive process, and in most cases, it's not really necessary for 99.9% of the people that are out there. So now that you understand why we do a Timken conversion, let's go do one. Okay, now I've already taken the bolts. If you remember from the last video, I had already split this case. This flywheel assembly had a tremendous amount of runout, and so I showed you examples of sumping, and we split this case and poured all of it out. So this case is obviously going to split very easy. I've already taken the bolts out, but I wanted you to see what you see on a stock case. So let's remove that. And that's the flywheel half. Spins around just like so. Now, because this bearing has the roller bearing in it, this flywheel assembly is going to lift right out of the case. Just like so. And this flywheel, this one is actually beyond being rebuilt, unfortunately, because the sprocket shaft on this side, remember I talked to you about the runout here and also the run out at the end of the shafts. Well, this shaft is actually out this direction here, as well as this one. I can almost see it visually that it appears if it's folding this way. I'm not sure if you can see that on the camera or not, but this is basically a boat anchor at this point. But I do want you to pay attention here to this. This is the bearing race for the I and A roller bearing that's pressed in. On the new one, that will have the tapered Timken half of the bearing set pressed onto there. Now let's take a look at this I and A bearing. See the rollers? You can also see on this half, this is the same bearing that's in here. You can just see the multiple rollers with the cage in there, and it just rotates around with the crank. Fairly straightforward. Pull a retaining ring. Now we'll flip it over. Now on this side, we're going to have the seal that will be pressed out. And then we'll press out the bearing. Now we've got the seal removed. One of the things that we're going to inspect, take a look in here, we're going to make sure there's no scarring or any issues inside the sealing surface there. And there are none. Now that we have our bearing out, let's inspect it. First, again, you can see as described, this is just a typical roller bearing, all right, pressed into this side of the case. It came out, this being the bottom of the bearing, down here. So let's take a close inspection, and we're gonna take a look at the case. Notice the discoloration on the bearing. Now, these small scratches in this area right here from it being pressed out of the case, galling and pulling a little bit of aluminum with it, which is not unusual. But notice the heat signature and the wear marks in this area here. Remember, this was at the bottom of the stroke. And we work our way around, see that it diminishes up to the top, and you don't see quite as much of it. All right, remember when we talked about the different forces on a crankshaft, as it's coming down at the bottom of the stroke, sweeping through, and then of course the force or resistance to rotation on the primary side with the primary chain and rear wheel, there's a tremendous amount of force that occurs in this area here. Okay, so this was the bottom of the bearing facing just like this, and we see that signature and the additional stress on the race in that area. And we're going to see the exact same thing in the case. Notice here, you see that same exact heat signature and wear pattern. Now let's rotate it around and look at the top. You don't see it as much. There in the top, it almost looks like raw machined aluminum. So all of your forces being down here. With that tapered Timken bearing, you're spreading these forces more equally between two bearings along the entire surface because it's a taper, instead of just focusing all of that pressure on one side of the bearing. So at this point, what we have to do is actually machine the case for a Timken Bearing Sleeve. Now this sleeve is what we'll be installing. Now, this is made by Jims Machine. It's actually a little known fact. Jims Machine, they weren't always just a tool company. Jims, if I'm not mistaken, got started making crank pins, and then it turned into them making tools and of course various other performance parts. But this is their Timken Bearing Conversion sleeve, and this is a fantastic way to do a Timken Bearing Conversion. This is made out of tool steel and precision ground, and what we have to do, this will go into this place here, again giving us a tool steel surface to then press the bearing race in for the Timken on both sides, so we're not being supported by the aluminum anymore. It's actually going to be on steel. This will be Loctited into place, but before we press this into place, there's some machining operations we have to do. So I have a setting fixture here that is also made by Jims Machine that will show me where I need to drill the holes. So we're going to drill and tap these 6 holes. Then we also have to drill oil supply holes, and there'll be an oil feed hole here and an oil drain hole there, and we have a fixture to do that. So let's pull that out. Of course, you'll notice the that on there, but remember who I said actually makes this particular tool. Jims Machine. It really is a great system for somebody that doesn't have a big machine shop. This made this job so much easier than Jim's coming up with this tool, because used to, and back when, used to have to machine the case and make the sleeves and do all this yourself, and this jig, yeah, you still have to go through machining processes, but this jig sure did make this a lot more economical for the average owner. Plus, they do little things like putting stop collars on each of the bits, so you don't really have to indicate in your mill or anything like that. And these are depth gauges, basically, so you can check your bits, check the depth, and it's a really great way to do it. Technically, yes, you could do this with a hand drill, but I'm not a hand drill kind of guy, so we're going to go over to my fancy drill press, otherwise known as a mill, and drill out each of these holes. Now, this is the oil drain and oil feed holes. We will do that with a hand drill, and it's easy to do it that way, and it's a drain hole. It's not necessarily a precision fitment. So let's go to the mill. I'll give you another little tip. If you're doing any kind of drilling at all, just a little tech tip, be it with a hand drill or regular drill press or whatever, and you're using a stop collar, if your chuck will allow it, take your stop collar and bump it up against the jaws in your chuck. That way, if your stop collar happens to slip, then it'll be at the known right depth. And of course, then when you're pulling down and drilling your holes, when it touches off, the stop collar can't slip. It's captive in there. Now that we've got our mounting holes drilled, we can drill for our oil feed and our oil drain. Now, if you remember the tip that I mentioned a minute ago, take your drill stop. Of course, we're going to check it against here. We've got the proper depth. Take your drill stop and run it all the way up to the chuck. Now we can do our oil feed hole. Okay, now that we've got our mounting holes drilled, our feed hole, our drain hole, we can remove this, then we'll tap each of the 6 holes. And here you can see again, the drain hole, feed hole drilled in at an angle. They come out just inside here, which feeds the bearing surface there. And then your drain is deeper down on the inside down there to circulate it through the bearing completely. Now, I like to do a little extra step with these. Anytime you tap a hole, when you start making that first cut, the thread will lift a little bit and leave a little bit of chip or slag on the surface here. Now, if we take a look at this piece, again, this is precision ground. This is very precise fit. This flat area here needs to be completely flat up against this surface here. So we're going to go back over to the mill and countersink each one of these holes. All right, now we got the holes countersunk, nice and smooth all the way around, perfect. I actually like to prefer to take the fixture back off, clean everything exceptionally well, using brake clean, make sure we've got a good surface there. You know, this thing is Loctited in with whole bearing and seal retention compound, so that's about as permanent as you can get. So we want to make sure to have a good clean surface there for it to adhere to. Also, we're going to be sure to use that brake clean and get down inside these threads. You can use Tap Magic, which is great for aluminum. I like this sulfur-based lubricant, but we need to make sure we get all of that out of there. Trusty brake clean. Now we need to clean this fixture because this is the press tool that will be used in conjunction with the Timken sleeve from Jims to press the sleeve into the case. All right, well, there we go, friends. That is the, ooh, got me a headache. That's the machining process in a nutshell. In the next video, we will press the sleeve into the case, we'll screw the thing down, and then we will install the flywheel assembly, and I'll show you how to set bearing in play. And that's a very critical, precise measurement that has to be done perfectly. So there may be 2 or 3 attempts to get that within the 0.5 thousandths of an inch tolerance that we're looking for in our full blueprints here. Thanks a million for watching and coming along for the ride. We've got a long way to go with this twin cam and M8 series, but we started from the top and we're working our way up. I'm sure you guys noticed wearing our new vintage Skunkworks shirt. I just put up another one yesterday. That's a bit of a throwback. So if you want a cool shirt, check out our Teespring store. We would appreciate it. As always, thanks a lot for watching. If I've earned your subscription, click the button, click the bell so you'll know when we upload the next video on finishing up this Timken Bearing Upgrade. Thanks a million, guys. Take care of yourselves and each other. Have a good one.